Think about this for a second. What if everything we see, everything we know, the entire universe with its countless galaxies, swirling nebulae, and blazing stars, began as something smaller than a single grain of sand? A moment so fleeting, so unimaginably dense and hot, that it defies everything our brains are wired to understand. That's the mystery of the universe's first moments, a cosmic magic trick played on the grandest stage imaginable, and we're still scrambling to decode how it all unfolded. Picture this: one instant there was nothing, no space, no time, no matter, and then, in less than a blink, an explosion of energy so violent that it set the stage for all of existence. We call it the Big Bang, but that name doesn't even come close to capturing the sheer strangeness of it. It's like trying to describe a symphony by only listening to the first note. Scientists have spent decades piecing together clues, hunting for answers in the faint whispers of ancient light and the tangled equations of quantum physics. And yet, the deeper we dig, the more questions we uncover. What sparked it? What came before? And most tantalizing of all, are there other universes out there, born from their own explosive beginnings? That's where things get wild. Over the years, brilliant minds have proposed not one, not 10, but 30 mind-bending theories about how the universe might have kicked into existence. Some sound like science fiction: cosmic bubbles colliding, ghostly membranes vibrating in higher dimensions, even a universe that cycles through endless deaths and rebirths. Others twist the very fabric of reality, suggesting time itself might not be what we think. And here's the crazy part: we don't know which, if any, are right. But that's what makes this journey so thrilling. Today, we're diving into these theories, unraveling the boldest, most fascinating ideas about how it all began. So buckle up, we're about to explore the edges of human understanding, where the laws of physics blur and the universe's deepest secrets wait to be discovered. The most iconic idea about our cosmic origins begins with a single, mind-warping concept: a singularity. Imagine all the energy and matter in the universe compressed into an unfathomably tiny point, smaller than an atom, hotter than any star, denser than anything science can describe. That's the Big Bang Singularity, the moment when time and space as we know them flickered into existence. But here's the twist: trying to picture what came before it might not even make sense. Time itself, the very framework of cause and effect, may have begun in that explosive instant. Asking what was before the Big Bang could be like asking what's north of the North Pole. It's a question that might not have an answer. This primordial seed of reality didn't explode into empty space, it created space. The universe didn't expand outward like a firework in a dark sky. The fabric of existence itself stretched, carrying matter along with it. And yet, the singularity remains a paradox. Even Einstein's equations break down when we try to peer into that initial moment. Gravity becomes infinite, the laws of physics as we know them dissolve, and we're left staring into a mathematical abyss. Some physicists argue that quantum mechanics, the strange rules governing the smallest particles, might hold the key to unraveling this mystery. Others suggest the singularity wasn't a true beginning at all, but a bridge from some deeper, hidden state of reality we've yet to uncover. And then there's the ultimate puzzle, the concept of nothingness. If the universe sprang from nothing, what does nothing even mean? Empty space, a void? Or something far stranger, perhaps a realm where time, space, and energy simply didn't exist yet? Some theories suggest that what we call nothing might actually be a seething quantum foam, where particles flicker in and out of existence spontaneously. Could our entire universe be the result of one such quantum fluctuation, magnified to cosmic proportions? The more we learn, the clearer it becomes the Big Bang wasn't just an event. It was the ultimate reset button, rewriting the rules of reality itself. If the Big Bang was the universe's first breath, cosmic inflation was its dizzying sprint into existence. a fraction of a second where reality stretched faster than the speed of light itself. This theory, dreamed up by physicist Alan Guth in the 1980s, suggests that moments after the singularity, space didn't just expand. It exploded outward with impossible speed, doubling in size over and over again, like a balloon inflating beyond comprehension. Think of it this way: if you scattered 2 dots of paint on a deflated balloon and then blew it up, those dots would zoom apart, not because they're moving, but because the fabric between them is stretching. Now imagine that balloon is the entire universe, and the inflation happens so fast that in less than a trillionth of a second, a speck smaller than an atom becomes larger than our observable cosmos. That's the mind-bending scale of inflation, a growth spurt so violent it left permanent wrinkles in the fabric of space-time, echoes we now detect as subtle temperature variations in the cosmic microwave background. But why did Guth propose something so extreme? It all comes back to a puzzle called the horizon problem. Look at the night sky in opposite directions, and you'll see regions of space so far apart that light hasn't had time to travel between them since the Big Bang. Yet somehow, these disconnected patches share identical temperatures and properties, like distant strangers wearing matching outfits. Inflation fixes this by suggesting that before the universe's wild expansion, everything was crammed into a tiny, ultra-connected region, close enough to even out, then flung apart in an instant. The implications are staggering. If inflation is real, our entire cosmos might be just one bubble in an endless froth of universes, each with its own laws of physics. Some could be collapsing while others bloom. Some might have 10 dimensions or stars made of dark matter, and here's the kicker: we may never know for sure. Inflation happened so early, so quickly, that its direct evidence is buried under layers of cosmic history. Yet its fingerprints are everywhere, from the flat geometry of space to the way galaxies cluster. It's a theory born from math, tested by observation, and still, after decades, the best explanation we have for why the universe looks the way it does, a fleeting moment of chaos that set the stage for everything. What if the Big Bang wasn't a one-time event, but just the latest chapter in an endless cosmic cycle, a universe that breathes in and out, expanding and collapsing over and over for eternity? That's the heart of the cyclic model, a theory as poetic as it is profound. Instead of a single explosive beginning, this idea suggests our universe is caught in an infinite loop of death and rebirth. Each cycle starts with a Big Bang, expands for billions of years, and then collapses back into a fiery crunch, only to explode anew. It's like a phoenix, but on the scale of all existence. One of the most striking versions of this idea comes from physicist Roger Penrose, who proposes something even wilder: evidence of past universes might be hiding in plain sight. He points to mysterious anomalies in the cosmic microwave background, the afterglow of the Big Bang, which he calls Hawking points. These faint, circular patterns, he argues, could be the ghostly imprints of supermassive black holes from a universe that existed before ours. Imagine finding footprints in the sand left by a creature no one's ever seen. That's the level of intrigue here. Critics dismiss these patterns as random fluctuations, but if Penrose is right, we're literally seeing echoes of a cosmos long gone. The cyclic model flips our linear view of time on its head. In the standard Big Bang story, the universe has a clear beginning and marches irreversibly toward heat death. But in this cyclical vision, there's no true start or finish, just an endless rhythm of creation and destruction. Some versions even suggest that each cycle resets the laws of physics slightly, meaning every new universe could have different constants, different particles, even different dimensions. It raises a haunting question. If this has happened infinite times before, how many versions of us have lived and died in universes we'll never know? Yet the cyclic model isn't without its challenges. For one, we don't fully understand what would trigger a big crunch or how a collapsed universe could rebound into a new Big Bang. Dark energy, the mysterious force accelerating our expansion, seems to be pushing the cosmos toward endless stretching, not collapse. And then there's entropy, the universe's tendency toward disorder. Each cycle should leave more chaos than the last, making infinite repetitions seem unlikely. But perhaps, as some theorists suggest, the bounce itself resets entropy, like shuffling a deck of cards back to order. What's mesmerizing about this idea is how it reframes our place in the cosmos. We might not be living in the first or last universe, but just one page in an endless book. It turns the Big Bang from a singular miracle into a heartbeat, one pulse in the life of something far grander. Whether Penrose's Hawking points hold the key or the cyclic model evolves into something new, one thing's certain: the universe's first moments might not have been first at all. They could be part of a story with no beginning and no end, written in the language of collapsing space, rebounding singularities, and the faint whispers of universes past. Now let's step into a theory so radical it turns our perception of reality inside out: the holographic universe. What if our three-dimensional world, with its towering mountains, swirling galaxies, and every atom in your body, is nothing more than a projection, a cosmic illusion painted onto a distant two-dimensional surface? It sounds like science fiction, but this idea emerges from one of the most perplexing puzzles in physics: the behavior of black holes. The story begins with a startling discovery about these cosmic monsters. When matter falls into a black hole, it vanishes from our universe, seemingly erasing information. A direct violation of quantum mechanics, which states that information can never be destroyed. Physicist Leonard Susskind, wrestling with this paradox, proposed a revolutionary solution. The information isn't lost at all. Instead, it's smeared across the black hole's event horizon, the point of no return, like a cosmic fingerprint pressed into a two-dimensional surface. From this boundary, all the complexity of the three-dimensional space within the black hole could be encoded, pixel by pixel. This realization birthed the holographic principle, the idea that our universe's entire contents might be similarly projected from a flat, distant boundary we can't see. To grasp this, picture a hologram sticker, tilt it in the light, and a three-dimensional image appears to float in midair, yet the entire image is contained on a flat, shiny surface. The holographic universe theory suggests reality works the same way. What we perceive as depth, volume, and movement could all be information painted on some vast, unseen cosmic canvas. Even stranger, the math suggests this isn't just a metaphor. The equations governing black holes and quantum gravity hint that the universe might literally operate this way, with every event, every particle, even your thoughts right now, existing as ripples on a hidden two-dimensional surface. Why would the universe bother with such a convoluted setup? The answer lies in efficiency. Storing information in two dimensions requires less space than three, a bit like compressing a movie file without losing quality. It's nature's way of cutting corners, a cosmic cheat code that might explain how our universe handles the mind-boggling complexity of gravity, quantum mechanics, and everything in between. Skeptics argue we're far from proving this idea, but experiments with high-precision lasers and even the cosmic microwave background are hunting for subtle distortions that could reveal the universe's pixelated underpinnings. If the holographic principle is true, it rewrites not just our origin story, but our entire understanding of existence. Space isn't an empty stage, it's a shimmering projection. Matter isn't solid, it's data, and the Big Bang, perhaps not a fiery explosion, but the moment this cosmic hologram flickered to life, a two-dimensional code unfolding into the illusion of depth, time, and everything we know. It's a humbling thought. We might not be living in the universe at all, but on its surface, like shadows dancing on a cave wall, mistaking the glow for the sun. What if our universe isn't just one cosmic story, but a single page in an infinite library of realities, each with its own laws, its own physics, its own version of existence? That's the breathtaking promise of the inflationary multiverse, a theory that takes the wild expansion of cosmic inflation and stretches it to its logical extreme. Imagine a bubbling cauldron of space-time where new universes sprout endlessly like bubbles in a boiling pot. Ours is just one bubble in an ocean of others, each born from the same runaway expansion that shaped our early cosmos. This idea starts with a tweak to inflation theory. Instead of stopping after our universe's explosive growth, what if space keeps inflating forever in some regions while pinching off into isolated bubbles elsewhere? Picture a loaf of rising raisin bread where each raisin is a universe. The dough keeps expanding infinitely, but individual raisins like our cosmos stop growing and cool into their own separate realms. In this scenario, the Big Bang wasn't a unique event. It was just one of countless eruptions in an eternally inflating mega-universe, a place where new realities are born constantly, each with random variations in their fundamental constants. That randomness leads to the most mind-bending part, the lucky lottery problem. Why does our universe have such finely tuned laws of physics, gravity just strong enough to hold galaxies together, a cosmological constant just weak enough to allow stars to form? If the multiverse is real, the answer might be chillingly simple. We live in the one bubble where conditions accidentally allowed life to exist. Other universes might collapse instantly, or have no atoms, or be filled with nothing but black holes. We don't see those failed experiments because, well, there's no one there to see them. It's like winning the cosmic jackpot, only the winners are around to marvel at their luck. But how could we ever prove something so vast, so hidden? Some physicists search for scars in the cosmic microwave background, faint imprints of collisions with neighboring bubble universes. Others look for strange anomalies in the distribution of galaxies, patterns that shouldn't exist in an isolated cosmos. So far, no smoking gun, but absence of evidence isn't evidence of absence. The multiverse might simply lie beyond our observational horizon, forever out of reach, and yet the implications haunt us. If true, this theory humbles our place in existence. Our universe isn't special, just statistically inevitable in an infinite ensemble. The constants we call laws might be nothing more than local bylaws, quirks of our tiny bubble. It's a dizzying thought. Somewhere out there, in the froth of eternal inflation, there could be a universe where gravity repels, where time runs backward, or where the very concept of physics is unrecognizable. We'll never visit them, never even glimpse them, but their existence or non-existence shapes how we understand our own cosmic home. The inflationary multiverse doesn't just stretch space. It stretches imagination, forcing us to confront the unnerving possibility that reality is far bigger, stranger, and more indifferent than we ever dared dream. If the inflationary multiverse wasn't mind-bending enough, buckle up, because string theory takes the idea of parallel universes and cranks it up to 11. Or rather, to 10 to the power of 500. That's a 1 followed by 500 zeros, a number so vast it dwarfs the atoms in our observable universe. According to string theory, the very fabric of reality might be woven from tiny, vibrating strings, and the way those strings wiggle could create not just one universe, but an almost infinite array of them, each with its own unique physics. Suddenly, scrolling through Netflix for something to watch doesn't seem so overwhelming. Here's how it works. At its core, string theory suggests that particles aren't just dots. They're microscopic loops of energy vibrating at different frequencies. The pitch of these vibrations determines whether a string becomes an electron, a quark, or a photon. But here's where it gets wild. To make the math work, string theory requires extra dimensions, not just the 3 we experience, but 6 or 7 more, curled up so small we'd never notice them. And the way those dimensions twist and fold, that's where the multiverse comes in. Imagine a cosmic landscape, a vast terrain of possible shapes for these hidden dimensions. Each valley, each peak in this landscape represents a different configuration, a different vacuum state with its own laws of physics. Some valleys might produce universes like ours with stable atoms and the right forces for life. Others might spawn chaotic realms where gravity is repulsive or time shatters into fragments. The kicker string theory estimates there are 10 to the 500 of these possible configurations. That's not just a multiverse, it's a megaverse, a fractal foam of realities so diverse it makes every sci-fi epic look tame by comparison. This idea, called the string theory landscape, flips the script on fine-tuning. Instead of asking why our universe's constants are so perfectly balanced for life, the answer becomes sheer probability. With that many possibilities, a handful of universes were bound to get it right by accident. The rest cosmic dead ends, unstable or barren, collapsing instantly or drifting empty. It's like a lottery where most tickets are duds, but with enough tickets, someone's bound to hit the jackpot. Of course, this raises a thorny question. If we can't see, touch, or test these other universes, is this even science? Some critics argue it's more philosophy than physics, a dazzling idea forever out of reach. But string theorists aren't giving up. They're hunting for subtle clues, perhaps a signature in the cosmic microwave background, or a particle behavior that only makes sense if extra dimensions are leaking into ours. Others suggest that gravitational waves from colliding brains, hypothetical membranes in higher dimensional space, might one day whisper proof of this sprawling multiverse. The wildest part, if string theory's landscape is real, then every possible version of reality might exist somewhere. A universe where gravity is 1,000 times stronger, where light never formed, where time runs in loops. Somewhere out there, in the cosmic kaleidoscope, there could even be a universe where you chose a different show to watch tonight, and another where the very concept of shows doesn't exist at all. It's a dizzying thought, one that stretches the limits of imagination. But in a cosmos this vast, perhaps the only thing more surprising than infinite possibilities is the idea that we're the only ones here. The idea of a universe that collapses only to rebound again, rising from its own ashes like a cosmic phoenix, is one of the most hauntingly beautiful theories in physics. What if the Big Bang wasn't the beginning, but just the latest bounce in an endless cycle of expansion and contraction? This is the heart of the bouncing universe theory, a radical alternative to the singularity's crushing finality. At its core, this idea challenges one of the biggest puzzles in cosmology: what happens when gravity becomes infinite? Classical physics breaks down at the moment of the Big Bang, leaving us staring into a mathematical void. But loop quantum gravity, a framework that blends quantum mechanics with Einstein's relativity, offers a way out. Instead of a singularity, a point of infinite density, this theory suggests that quantum effects create a sort of cosmic trampoline. When the universe contracts to a certain threshold, these quantum forces push back, triggering a rebound. Picture squeezing a stress ball until it suddenly springs open in your hand. That's the bounce, a moment where collapse reverses into explosive renewal. The implications are staggering. If the universe has bounced before, our entire cosmic history could be just one chapter in an epic with no beginning or end. Each cycle might last tens of billions of years, with galaxies forming, stars burning out, and black holes evaporating only for everything to collapse, rebound, and start anew. Some versions of the theory even suggest subtle traces of past universes could linger like cosmic scars. Imagine finding cracks in the cosmic microwave background that hint at a previous cycle's collapse, or detecting unusual gravitational wave patterns that echo the bounce itself. But how could a universe rebound without violating the laws of thermodynamics? After all, entropy, the measure of disorder, always increases. Wouldn't each cycle grow messier than the last? Here's the twist: the bounce might act like a cosmic reset button. Quantum effects during the rebound could reorganize matter and energy, effectively cleaning the slate for the next cycle. It's like shaking a snow globe. The chaotic flakes settle into a fresh, pristine scene. The bouncing universe isn't just a mathematical curiosity. It reshapes how we think about time, existence, and our place in the cosmos. If true, the Big Bang wasn't creation, it was transformation. And the next bounce, perhaps it's already written into the fabric of reality, waiting billions of years in the future, or maybe unfolding right now in some distant corner of the multiverse. The universe might not have a single story, but an infinite anthology, each volume ending with a collapse and every new beginning written in the ashes of what came before. What if everything we think we know about the universe's birth is wrong, and the real cosmic architect isn't gravity but electricity? That's the bold claim at the heart of plasma cosmology, a radical theory that tosses out the Big Bang and rewrites the universe's origin story with bolts of cosmic lightning. Pioneered by Nobel Prize-winning physicist Hans Alfvén, this idea paints a universe not of singularities and inflation, but of swirling currents and electromagnetic storms stretching across billions of light years. Picture the cosmos as an unfathomably vast circuit board. Instead of galaxies drifting aimlessly through empty space, Alfvén saw them strung along colossal filaments of ionized gas, cosmic power lines crackling with electricity. These plasma threads, stretching millions of light years, behave like high-voltage wires, twisting and knotting under electromagnetic forces. When currents surge, they pinch the plasma into glowing knots, which Alfvén argued could birth stars and galaxies without any need for a Big Bang. It's a vision of the universe where magnetism, not gravity, calls the shots, where the same forces that light neon signs on Earth also sculpt the largest structures in existence. Why don't more scientists embrace this electrifying alternative? Mainstream cosmology dismisses plasma universe theory for a few key reasons. First, while plasma dominates the visible universe, making up over 99% of observable matter, the Big Bang model relies on dark matter and dark energy, unseen entities that plasma cosmology outright rejects. Second, Alfvén's framework struggles to explain the cosmic microwave background, that telltale glow from the early universe that's considered smoking gun evidence for the Big Bang. Plasma cosmologists counter that the glow could come from other sources, like ancient stellar radiation absorbed and re-emitted by intergalactic plasma. But without a mathematical framework as precise as general relativity, the theory remains on the fringes. Yet the plasma universe keeps sparking debate, especially when we look at the cosmos' actual structure. Modern telescopes reveal galaxies clustered along sprawling filaments, eerily similar to Alfvén's predictions. Even more striking, some of these filaments glow with faint magnetic fields, threads of force that shouldn't exist if gravity alone shaped the universe. Could these be remnants of cosmic currents, fading power lines from an earlier epoch? Skeptics argue these structures form naturally under gravity's pull, but plasma proponents see echoes of Alfvén's lightning-filled cosmos. At its core, the plasma universe forces us to question which forces truly govern reality. Gravity might dominate at planetary scales, but in the seething, ionized depths of space, electromagnetism could hold the real power. It's a reminder that sometimes the most revolutionary ideas aren't those that add to our knowledge, but those that dare to tear it down and start fresh, even if it means rewriting the universe's first moments with bolts of celestial lightning instead of a single primordial bang. Here's a theory that flips the script on cosmic origins. What if our universe wasn't born from nothing, but from the belly of a black hole in another, older reality? This is the black hole genesis hypothesis, a spine-tingling idea that ties the birth of our cosmos to the most enigmatic objects in existence. Picture a black hole in some distant universe, its event horizon swallowing matter and energy beyond the point of no return. But what if, instead of vanishing into oblivion, that collapsing material birthed an entirely new space-time, a universe of its own, hidden behind the singularity? That's the core of this theory, black holes as cosmic wombs, each one potentially spawning a fresh reality with its own unique physics. The idea gained traction thanks to physicist Lee Smolin, who proposed a wild twist: black holes might not just create universes but evolve them. In his fecund universes theory, every black hole becomes a big bang for a new cosmos, with the laws of physics slightly tweaked in the process. Universes that produce more black holes would, in turn, spawn more offspring, leading to a kind of cosmic natural selection. Over countless generations, universes fine-tuned to maximize black hole production would dominate the multiverse. It's survival of the fittest, but on a scale so vast it makes Darwin's theory look like a footnote. But how could a black hole, a place where time and space seemingly break down, give rise to an entire universe? The key might lie in entropy, the measure of disorder. Black holes are entropy powerhouses, packing unimaginable amounts of chaos into their tiny singularities. Some theories suggest that inside a black hole, space-time gets so scrambled that it effectively reboots, birthing a new expanding universe in the process. Think of it like a cosmic pressure cooker. When matter gets crushed beyond comprehension, the laws of physics might reach a breaking point, triggering a new inflationary explosion. And here's where it gets even stranger. If this theory is correct, our universe could be nested inside a black hole from a parent cosmos, which itself might be inside an even older black hole ad infinitum. Its turtles all the way down, except the turtles are universes and the shells are event horizons. This would also solve a long-standing puzzle. Why does our universe seem so finely tuned for complexity? If Smolin's right, it's because we're the product of countless generations of cosmic trial and error, a universe optimized by black hole production through sheer statistical inevitability. Of course, skeptics raise valid questions. How could we ever observe evidence of a parent universe's black hole when, by definition, it lies beyond our cosmic horizon? Some researchers speculate that traces might linger in the cosmic microwave background, subtle imprints of the black hole's birth pangs. Others suggest that the initial spin of our universe, if it matches certain predictions, could hint at its origins in a rotating singularity. But for now, these ideas live in the realm of tantalizing speculation, pushing the boundaries of what we dare imagine about reality's deepest roots. The black hole genesis theory doesn't just reshape our understanding of the Big Bang. It turns black holes from cosmic dead ends into portals, from destroyers into creators. If true, every black hole in our universe could be a budding cosmos, a hidden universe in waiting. And that raises a humbling thought. Somewhere out there, in the infinite depths of space-time, another civilization might be staring at the night sky, wondering if their reality, too, was born from the darkness of a singularity. What if everything you've ever known, the taste of morning coffee, the warmth of sunlight, even the vast, glittering expanse of the cosmos, is nothing more than lines of alien code running on some unfathomable supercomputer? That's the spine-chilling premise of the simulation hypothesis, a theory that reframes reality itself as an ultra-advanced virtual construct. It sounds like the plot of a sci-fi blockbuster, but serious thinkers like philosopher Nick Bostrom and tech mogul Elon Musk argue it might be closer to truth than fiction. Bostrom's groundbreaking paper lays out a trilemma: three possibilities, one of which must be true. Either one, nearly all civilizations at our level of technological development go extinct before achieving post-human status. Or two, those that survive almost never bother to run ancestor simulations, high-fidelity recreations of their past. Or three, we're almost certainly living in a simulation right now. The logic is unsettlingly simple. If future civilizations have the computing power to simulate conscious beings, and they choose to run even a fraction of those simulations, the number of simulated minds would dwarf those in base reality. Statistically, the odds tilt overwhelmingly toward us being one of those simulations. Elon Musk takes it further, bluntly stating the chances we're in base reality are 1 billion to 1. His reasoning: look at the exponential leaps in gaming graphics, from pixelated Pong to photorealistic virtual worlds in just 50 years. Now project that progress another 10,000 years. If any civilization reaches the point of creating indistinguishable simulations, the number of artificial universes would explode like a cosmic Russian nesting doll, with each simulation potentially containing its own nested simulations. The idea that we're at the very top of that pyramid, the original reality, starts to feel vanishingly improbable, but how could we ever test such a dizzying claim? Some physicists suggest hunting for glitches in the fabric of reality, tiny errors akin to a computer rounding numbers. Others propose that the Planck length, the smallest measurable unit of space, might be evidence of a pixelated universe like the resolution limit of a cosmic GPU. Even quantum indeterminacy, where particles exist in fuzzy superpositions until observed, could be seen as a rendering optimization processing only what's necessary to maintain the illusion, like a video game loading textures as you turn your head. Yet the simulation hypothesis isn't without its critics. Many scientists argue it's unfalsifiable, a clever thought experiment with no empirical teeth. Others point out that simulating every atom in a universe would require absurd amounts of energy, making the idea pragmatically absurd. But simulation proponents counter that an advanced civilization might not simulate every quark, just the perceptual experiences of conscious beings, like a hyper-realistic dream. Whatever the truth, this theory forces us to confront fundamental questions about existence. If we're in a simulation, who coded it? Is it an alien anthropology project, a cosmic schoolhouse for souls, or just some post-human teenager's history homework? The eerie beauty of the simulation hypothesis is that it doesn't diminish reality. It expands it, turning the universe into the ultimate mystery box, hiding secrets even its creators might not fully understand. Close your eyes and try to remember yesterday. Feels real, doesn't it? Now imagine being told that yesterday, along with tomorrow, and even the concept of before and after, might be nothing more than an elaborate illusion. This is the radical proposition of physicist Julian Barber's timeless universe, a theory that strips away time entirely, leaving only an endless, infinite now. Barber's idea turns our intuition inside out. We experience life as a sequence, a relentless march from past to future. But what if that flow is just a trick of perception? Picture a flipbook. Each page holds a static image, but when you flip through them rapidly, the still frames create the illusion of motion. Barber argues the universe works the same way. What we call time might just be the brain stitching together a series of frozen moments, each a complete configuration of the cosmos he calls a now. In this view, the Big Bang isn't an event in the past, it's simply one of countless nows, sitting statically in a vast landscape of possible universes. The implications are dizzying. Without time, there's no before the Big Bang, no after heat death, just an eternal gallery of cosmic snapshots. Your childhood, your future, even the dinosaurs aren't gone or yet to come. They exist in other nows, like unflipped pages in the book. This challenges Einstein's block universe, where past, present, and future coexist but remain woven into a four-dimensional space-time fabric. For Barber, there's no fabric at all, just isolated frames with no director, no reel, no projector. Critics argue this leaves no room for causality. How can one now influence another if time doesn't connect them? Barber's answer lies in the mathematics of shape-space, an abstract realm where time emerges from relationships between objects. When you watch a pendulum swing, its position changes relative to its surroundings, creating the illusion of time passing. Similarly, the universe's nows might be ordered by their relational geometry, not some external clock. It's like reading a novel by shuffling its pages. The story only makes sense if you arrange them correctly. But how does this explain our visceral experience of time's flow? Barber suggests consciousness itself might be the glue, stitching together nows into a coherent narrative. Each moment feels connected because your brain constructs continuity, much like a film editor splicing scenes. Even the arrow of time, why we remember the past but not the future, could be a quirk of entropy, with higher disorder nows appearing as later in our mental timeline. This theory doesn't just reshape cosmology, it redefines existence. If Barber is right, the universe isn't a story unfolding. It's a museum where every moment hangs forever, and we're just visitors walking through the halls, mistaking the exhibits for a moving picture. Time's river becomes a hall of mirrors, each reflection a complete world, and our journey through them nothing more than a breathtaking trick of perspective. Imagine waking up one day to discover that the entire universe is just one slice of bread in an endless cosmic loaf, and that the Big Bang was nothing more than a violent crash between slices. That's the essence of the ekpyrotic universe, a theory so elegant it rewrites the origin story of everything without invoking a single singularity. This idea emerges from the cryptic depths of string theory, where our three-dimensional world might be a membrane or brain floating in a higher dimensional space. And according to this model, the spark that ignited our universe wasn't an explosion from nothing. It was a collision between our brain and another, like two sheets of paper smacking together in an unseen wind. The brilliance of the ekpyrotic model lies in what it avoids. Unlike the classic Big Bang, which hits a dead end at the singularity, this theory offers a clean slate. Picture two brains drifting through an extra-dimensional void, drawn together by an invisible force. When they collide, the energy of impact gets funneled entirely into our four-dimensional realm, creating the seething plasma of particles we now call the Big Bang. No infinite densities, no breakdown of physics, just a transfer of energy so colossal it mimics creation itself. It's as if the universe hit the reset button by smashing into its cosmic neighbor. But here's where it gets even more intriguing. The ekpyrotic scenario isn't a one-time event. These brains might oscillate, cycling through phases of collision and separation over eons. Each crash could birth a new universe, meaning our cosmic history might be stuck on repeat, an endless cycle of cosmic bumper cars. And because the brains stretch infinitely, the collision wouldn't happen at just one point. The energy release would cascade across space, explaining why the universe looks so uniform in every direction we observe. No need for inflation. The collision's sheer scale smooths everything out naturally. Critics, of course, raise eyebrows. How do we test something happening in dimensions we can't perceive? Supporters argue that gravitational waves, ripples in space-time, might carry fingerprints of brain dynamics. Others hunt for unusual patterns in the cosmic microwave background, subtle asymmetries that could hint at a directional shove from the collision. But the real allure of this theory isn't just its answers, it's the questions it forces us to ask. If our universe is a brain, what else shares this higher dimensional space? Are there other collisions, other universes, lurking just beyond the edge of perception? The ekpyrotic universe doesn't just reimagine the Big Bang, it turns reality into a hall of mirrors where every reflection might be another cosmos brushing against our own. Imagine a universe where death is an illusion, where black holes don't erase information but quietly pass it along, like cosmic scribes etching the final chapter of one reality into the opening lines of the next. This is the stunning vision of Roger Penrose's conformal cyclic cosmology, a theory as poetic as it is profound. While most models treat the Big Bang as the ultimate starting line, Penrose flips the script entirely. What if the end of our universe isn't a cold, dark fade-out, but the prelude to another Big Bang, a cosmic encore fueled by the very black holes we thought were tombs? At the heart of this idea lies a radical reimagining of infinity. As our universe expands toward heat death, galaxies scatter, stars burn out, and black holes slowly evaporate through Hawking radiation. But in this final act, something unexpected happens. With no matter left to curve spacetime, the universe becomes featureless, stretched so thin that distances and time lose all meaning. Penrose argues this emptiness mathematically mirrors the smoothness of the Big Bang Singularity. In this bizarre state, the end of time loops back to the beginning, and the dying universe seamlessly becomes the seed of a new one. No singularity, no creation from nothing, just an infinite cycle of resets, each triggered by the utter stillness of what came before. But how does information survive this cosmic recycling? Here's where black holes play the starring role. In standard physics, black holes appear to destroy information, violating quantum mechanics. Penrose proposes the opposite. These gravitational monsters aren't shredders but archivists. As they evaporate, they imprint their data onto the fabric of spacetime itself, leaving faint marks called Hawking points, cosmic birthmarks from a previous universe. These would appear as faint, circular patterns in the cosmic microwave background, subtle bruises where ancient black holes once pulsed with energy. The scientific community remains split. Penrose and his collaborators claim to have spotted these Hawking points in CMB data rings of polarized light that defy conventional explanations. Skeptics counter that these patterns could be random noise or artifacts of data processing. But if verified, the implications would rewrite cosmology. We might literally be staring at the fingerprints of a universe that existed before ours, its black holes whispering secrets across eternity. What's mesmerizing about conformal cyclic cosmology isn't just its elegance, but its humility. It suggests our universe isn't special, just one link in an endless chain, each cycle inheriting remnants of the last. Every black hole we observe, from tiny stellar ones to supermassive beasts at galactic cores, could someday seed new realities, their encoded information blossoming into fresh laws of physics, new particles, perhaps even alien civilizations oblivious to the cosmic debt they owe to our fading sky. The theory doesn't just challenge our understanding of origins, it turns existence itself into an Ouroboros, a snake forever eating its own tail, where endings are beginnings and nothing, not even time, is ever truly lost. Einstein once scribbled a tiny, seemingly insignificant term in the corner of his equations, a mathematical fudge factor he called the cosmological constant. He added it to keep the universe static, eternal, and unchanging, because back in 1917, everyone knew the cosmos was timeless. Then Hubble proved the universe was expanding, and Einstein famously called his constant his greatest blunder. But what if he was right the first time? What if the universe is eternal, not in the way he imagined, but in a far stranger, more modern sense? Enter the static universe theory, a radical revival of the steady-state model with a dark energy twist. At first glance, the idea seems absurd. We've all seen the Hubble images, galaxies flying apart, the afterglow of the Big Bang stamped across the sky. But look closer. Dark energy, that mysterious force accelerating the expansion, might be doing something unexpected, stretching space so fast that it creates the illusion of change while keeping the universe fundamentally static on the largest scales. Picture a treadmill set to light speed. You're running full tilt, yet staying in place. Now imagine every galaxy is a runner, and dark energy is the treadmill hurtling everything outward so uniformly that the cosmic density never actually changes. New particles flicker into existence to fill the gaps, maintaining perfect equilibrium. It's a universe that looks dynamic but is, in its bones, frozen. This isn't your grandfather's steady-state theory. The original version, championed by Fred Hoyle in the 1950s, proposed continuous creation of matter to balance expansion. Critics shot it down when the cosmic microwave background revealed the Big Bang's aftermath. But dark energy rewrites the rules. If space stretches exponentially, regions beyond our horizon could be spawning new matter, not in dribs and drabs, but in vast, self-replenishing waves. And here's the kicker. In an infinite expanse where space grows faster than light can traverse it, the observable universe resets. galaxies cross the horizon and vanish, while quantum fluctuations in the void birth fresh ones. The result, a cosmos that's eternally new, yet statistically identical at every epoch, a perfect cosmic sleight of hand. Critics pounce on the fine-tuning required. Why would dark energy's strength balance matter creation so precisely? Proponents counter that this balance might not be coincidence but necessity. A universe that doesn't stabilize this way would collapse or tear apart long before life could arise. It's the anthropic principle with a twist. We don't observe a changing universe because only a static-seeming one allows observers to exist. The eerie beauty of this idea is how it flips our obsession with origins. No Big Bang, no heat death, just an endless self-adjusting now. Einstein's abandoned constant might yet have the last laugh, not as a mistake but as a prophecy. The universe isn't evolving. It's pretending to. Here's one of the strangest ideas in theoretical physics. What if the universe didn't come from a singularity or a collision, but from a tiny hiccup in the void itself? This is the quantum fluctuation theory, and it turns the cosmic origin story into something far wilder. A cosmic jack-in-the-box, where reality springs into being not from a grand explosion, but from the fizzing, unstable depths of nothingness. At the heart of this idea lies a bizarre quirk of quantum mechanics. Empty space is never truly empty. Even in a perfect vacuum, particles flicker in and out of existence like bubbles in a cosmic soda. These virtual particles borrow energy from nowhere, exist for a fleeting instant, then vanish, all within the strict rules of quantum uncertainty. Normally, these fluctuations cancel out almost instantly. But what if, in some inconceivably rare moment, one didn't? What if a quantum blip borrowed just enough energy to inflate into an entire universe? It sounds like science fiction, but the math checks out. The zero-point energy of the vacuum, the lowest possible energy state, isn't zero. It's a seething, probabilistic froth where particles wink in and out constantly. Under the right conditions, this quantum foam could bubble up something far larger, a pocket of space-time swelling uncontrollably into a cosmos. Picture a tiny seed of distortion, a wrinkle in the void's fabric that grows and grows until it becomes self-sustaining, pinching off from the quantum background like a soap bubble detaching from a wand. That's the birth of a universe, not with a bang, but with a probabilistic whisper. This raises a mind-bending question: is nothing inherently unstable? We tend to think of emptiness as serene, static, but quantum physics paints it as a roiling, chaotic sea. If the void can spontaneously generate particles, why not entire universes? Some theorists take this even further, suggesting that our cosmos might be just one bubble in an eternal quantum foam, where universes pop into existence constantly, each with its own random laws. Most would collapse instantly or fizzle into oblivion, but by sheer chance one might strike the right balance to endure, a cosmic lottery where our universe is the lucky ticket. Of course, skeptics pounce on the biggest hurdle. How do you test this? If universes bud off from an inaccessible quantum realm, we might never observe direct proof. Yet there are tantalizing hints. The cosmic microwave background's faint irregularities could carry echoes of that initial fluctuation. Or perhaps the universe's overall geometry, its flatness, its uniformity hints at a quantum origin. And if this theory is true, it rewrites the meaning of nothing. The void isn't sterile ground, it's fertile, bubbling with potential universes waiting for their moment to burst forth. The quantum fluctuation theory doesn't just challenge how we picture the Big Bang, it upends our whole notion of beginnings. There's no first cause, no prime mover, just the capricious whims of quantum physics, turning emptiness into everything we know. It's a humbling thought. Our vast cosmos, with its galaxies and black holes and spinning planets, might owe its existence to a random tremor in the dark, a fleeting ripple that, against all odds, became the canvas for reality itself. The universe might not be the three-dimensional masterpiece we perceive. It could be a cosmic illusion, a hologram projected from a hidden two-dimensional surface at the very edge of reality. This is the mind-bending premise of the holographic Big Bang, a theory that rewrites the birth of everything as the ultimate data unpacking event. Picture the Big Bang not as a fiery explosion, but as the moment a cosmic QR code flickered to life, translating flat, encoded information into the sprawling, multidimensional reality we now inhabit. At the heart of this idea is a startling discovery about black holes. When matter falls into one, it doesn't just vanish. Its information gets smeared across the event horizon, the black hole's two-dimensional boundary. Physicists realized this wasn't just a quirk of gravity. It hinted at a deeper truth. If a black hole's entire three-dimensional interior can be described by data painted on its two-dimensional surface, could the same be true for the universe? The holographic principle suggests yes. Our entire cosmos, every galaxy, every atom, every thought might be a projection from a flat, distant screen we can't see, like a movie playing on the walls of an immeasurable cosmic theater. Now apply this to the Big Bang. Instead of a singularity bursting forth in three dimensions, imagine a two-dimensional surface, a vast primordial hard drive, encoding the blueprint for reality. In this scenario, the bang wasn't an explosion of matter, but a decoding of data. The universe booted up, translating abstract information into the physics, chemistry, and even consciousness we experience today. It's like running a video game. The graphics feel three-dimensional, but they're rendered from lines of code stored on a flat chip. Our reality could be the ultimate simulation, not running on silicon, but on the fundamental laws of quantum gravity. This theory doesn't just reshape our cosmic origin story, it redefines existence itself. If true, the Big Bang wasn't the beginning of space and time, but the moment a hidden layer of reality expressed itself in a form we could perceive. The implications ripple outward. Black holes might be glitches in the cosmic rendering, dark energy could be a memory leak in the system, and even time itself might just be a side effect of how the data streams. Skeptics argue it's untestable, but supporters point to faint anomalies in gravitational wave detectors or patterns in the cosmic microwave background as potential fingerprints of the universe's pixelated origins. The eeriest part, if the holographic principle holds, we're not just living in a universe, we're living on its shadow. Every star, every breath, every moment of history is just ink on a cosmic page we'll never see. A story written in two dimensions but experienced in three. It's a humbling thought. The Big Bang might not have been creation but translation, the universe learning how to read itself aloud. What if the universe holds a hidden mirror world, one where every particle we know has a secret twin, perfectly balanced but invisible to our best detectors? This is the tantalizing promise of supersymmetry, a theory so elegant it could solve multiple cosmic mysteries at once. Known affectionately as SUSY to physicists, it proposes that every known particle, electrons, quarks, photons, has a heavier, undiscovered superpartner. These shadowy twins might be the missing puzzle pieces, quietly maintaining cosmic order since the universe's first moments. The math behind SUSY is breathtakingly simple in its symmetry. It suggests that the fundamental forces we observe today, gravity, electromagnetism, the strong and weak nuclear forces, were once perfectly balanced in the early universe, unified under unimaginable temperatures. But as the cosmos expanded and cooled, that symmetry broke, leaving us with the fractured physics we now study. SUSY particles could be the glue that once held it all together, relics of that primordial harmony. And here's the kicker: one of these superpartners might be the elusive dark matter, the invisible scaffolding that shapes galaxies yet refuses to interact with light. For decades, physicists have chased these spectral twins, convinced they're lurking just beyond our reach. Particle colliders like the Large Hadron Collider have smashed protons at nearly light speed, hoping to spawn a SUSY particle in the wreckage. Detectors buried deep underground wait for the faintest whisper of a superpartner bumping into ordinary matter. So far, nothing. The absence of evidence has turned Sussy into a running joke, the theory of everything that stubbornly refuses to show up. Some researchers whisper that Sussy might be in crisis, its most optimistic predictions gathering dust. Others insist we're simply looking in the wrong places, like archaeologists sifting through the wrong layer of sediment. Yet the theory's beauty keeps it alive. Sussy doesn't just tidy up particle physics. It could explain why the Higgs boson is so suspiciously light, or why gravity is laughably weaker than the other forces. Without supersymmetry, the math behind the Higgs suggests the universe should have collapsed in on itself long ago, unless some hidden mechanism like Sussy particles quietly cancels out the instability. It's like discovering your bank account should be empty, yet somehow there's money in it, and Sussy is the invisible deposit keeping the cosmic books balanced. The hunt continues, fueled by equal parts frustration and hope. If Sussy particles exist, they might be hiding in plain sight, camouflaged by their sheer mass or fleeting existence. Or perhaps they've decayed into even stranger forms, leaving only faint traces in high-energy collisions. One thing's certain, finding them would rewrite the story of the universe's birth, revealing a hidden symmetry woven into reality's fabric. Until then, Sussy remains the universe's most tantalizing ghost story, a theory too compelling to abandon, yet too elusive to prove. And who knows, the next particle collision might finally unveil the mirror world we've been missing all along. Deep in the cosmic void, something impossible is happening. Galaxies are fleeing, not just drifting apart with the universe's expansion, but racing en masse toward a single patch of nothingness, like leaves caught in a hidden current. Astronomers call it the dark flow, and it defies everything we know about how the cosmos should behave. The story begins with galaxy clusters, colossal structures containing thousands of galaxies bound by gravity. When scientists mapped their motions using X-ray telescopes and the cosmic microwave background, they expected to see chaos, a random scattering of velocities. Instead, they found hundreds of clusters all moving in the same direction at staggering speeds, over 2 million miles per hour, toward a point near the constellations Centaurus and Vela. It's as if some invisible hand is tugging at the fabric of reality itself. What could possibly exert such a pull? The unsettling answer: nothing inside our universe should. The scale of this motion dwarfs even the Great Attractor, a known supercluster with immense gravity. Calculations suggest the force required would need to come from beyond the observable universe, from something so massive and distant that light from it hasn't reached us in 13.8 billion years. That's where things get spine-tingling. One radical explanation: the dark flow might be evidence of another universe brushing against ours. In the multiverse theories we've explored, bubble universes float in a higher dimensional space, occasionally nudging one another. If a neighboring cosmos collided with ours long ago, the gravitational aftershock could still be dragging galaxies toward the impact zone. Picture two soap bubbles touching in a sink. The spot where they meet would ripple inward, just like these galaxy clusters. Critics argue it could be a statistical fluke or a subtle error in measurements, but the data persists across multiple studies, even as probes like Planck refine our cosmic maps. If the dark flow is real, it's more than a curiosity. It's a crack in the door of our cosmic isolation, a hint that we're not alone in the greater multiversal ocean. And out there, in the unfathomable dark, something immense is calling. What if gravity, the force that pins us to Earth and binds the cosmos together, isn't a fundamental force at all, but a side effect of something far stranger? That's the provocative claim at the heart of Eric Verland's entropic gravity, a theory that rewrites the laws of physics by treating gravity as an illusion emerging from the universe's hidden chaos. Forget curved spacetime or attracting masses. Gravity, in this radical view, is more like a cosmic mirage, a trick played by the relentless march of entropy. the universe's tendency toward disorder. Verlaine's idea starts with a simple but profound question. Why does gravity behave the way it does? Instead of invoking warped geometry like Einstein or invisible particles like dark matter theorists, he points to entropy, the same force that makes ice melt and coffee cool. Think of the universe as a vast, interconnected network of microscopic bits, each holding information. When matter disturbs this network, say, a planet sitting in space, it creates a sort of information debt, a region where entropy must increase to balance the books. The universe, always seeking equilibrium, responds by pushing nearby objects toward that disturbance. That push, we call it gravity. It's not a force but a statistical tendency, like how heat flows from hot to cold, not because of some heat force, but because it's the most probable outcome. This framework does something astonishing. It makes dark matter obsolete. For decades, astronomers have invoked dark matter to explain why galaxies rotate faster than Newton's laws predict. But Verlaine argues we don't need invisible particles, just a misunderstanding of gravity's true nature. In his equations, the extra pull attributed to dark matter emerges naturally from entropy's grip on the universe's underlying structure. Picture a fish trying to understand water by only seeing its ripples. Dark matter might be our clumsy attempt to explain ripples while missing the fluid itself. The implications ripple deeper. If gravity is entropic, the universe might be pixelated at its core, built from discrete bits of information like a cosmic computer screen. This aligns eerily with ideas like the holographic principle, where reality is a projection from a two-dimensional surface. In Verlaine's view, these pixels, these fundamental units of information aren't just passive dots but active participants, constantly shuffling to maximize entropy. Gravity becomes a collective behavior, like the way a murmuration of starlings moves as one. Even though no single bird is calling the shots, critics, of course, aren't convinced. Entropic gravity struggles to explain certain observations, like the precise lensing of galaxy clusters, and without a smoking gun, some experimental proof that gravity truly emerges from entropy, many physicists cling to dark matter as the safer bet. But Verlaine's theory lingers because it dares to ask the heretical question: what if we've been staring at the shadow of gravity, not the thing itself? It turns the universe into a dynamic, evolving computation, where the forces we take for granted are just emergent patterns in the chaos. Whether he's right or not, entropic gravity forces us to confront a humbling possibility that the cosmos might be playing a game whose rules we're only beginning to guess. Now consider this unsettling possibility. What if your thoughts, your memories, even your perception of this very moment aren't the product of billions of years of evolution, but a fleeting accident in an endless cosmic void? This is the nightmare fuel known as the Boltzmann brain paradox, a thought experiment so bizarre it makes the simulation hypothesis seem almost cozy. It all starts with a simple question. In an infinite universe governed by entropy, what's stopping random particles from spontaneously arranging themselves, just for an instant, into a fully self-aware consciousness? The idea springs from Ludwig Boltzmann's 19th century work on statistical mechanics, which revealed that even in chaos, tiny pockets of order can emerge purely by chance. Given enough time, and the universe has plenty, particles could theoretically assemble into anything, from a perfect replica of the Mona Lisa to a functioning human brain, complete with fabricated memories of a life never lived. These hypothetical freak occurrences are dubbed Boltzmann brains, and they raise a disturbing implication. If random, self-aware blips are statistically more likely than the orderly 13.8 billion year march from Big Bang to human civilization, then we might be the flukes, not the universe. Think of it like shaking a box of Scrabble tiles forever. Eventually, they'll spell out Shakespeare, but they're infinitely more likely to form a single coherent word by accident than an entire play. Similarly, in an eternal cosmos, fleeting moments of awareness outnumber persistent, structured life by unimaginable margins. So why does reality feel so stable? Why do our memories align so neatly with historical records and physical laws? The chilling answer might be that they don't. We're just momentary aberrations hallucinating coherence before dissolving back into the void. Physicists recoil from this idea not because it's unsettling, but because it's possible within known physics. Theoretically, quantum fluctuations could birth a disembodied brain with false memories of typing this sentence or of reading it. The odds are astronomically low, but infinity doesn't care about odds. This is where cosmology collides with philosophy. If Boltzmann brains dominate the statistical landscape, why don't we observe them? Some argue that their fleeting existence leaves no trace, making them irrelevant. Others propose that the very fact we're debating this disproves the idea, because Boltzmann brains would almost certainly hallucinate simpler, nonsensical realities, not a universe with consistent laws. Yet the paradox lingers, a ghost in the machinery of reality. It forces us to confront the fragility of our assumptions. Maybe the universe isn't ancient, just felt that way by a brain born yesterday. Or perhaps entropy's grip isn't absolute, and true order emerges more easily than randomness. Whatever the answer, the Boltzmann brain reminds us that in a cosmos governed by statistics, even existence itself might be a roll of the dice, one we're either impossibly lucky to witness or tragically mistaken to believe in at all. Picture the universe stretching faster and faster, an unstoppable expansion, not just pushing galaxies apart, but eventually tearing apart stars, planets, even atoms themselves. This is the nightmare scenario of phantom energy, the most extreme and violent flavor of dark energy imaginable. Unlike ordinary dark energy, which accelerates the universe's expansion at a steady pace, phantom energy grows stronger over time, as if the cosmos is pressing down on the gas pedal with no brakes in sight. The math behind this leads to something called the Big Rip, a cosmic doomsday where expansion doesn't just win, it annihilates. Here's how it works. Right now, dark energy's grip is gentle enough that gravity still holds galaxies, solar systems, and even your coffee cup together. But if dark energy isn't constant, if it's phantom energy, intensifying as space stretches, then its power will eventually overwhelm every force in nature. First, galaxy clusters will be ripped apart, flung into the void so fast that their light could never reach us again. Then, gravity would lose its grip on individual galaxies, stars drifting alone in an ever-expanding darkness. But the true horror comes later. About 2 months before the end, phantom energy's pull would overcome the bonds holding our solar system together. Planets would be yanked from their orbits, Earth torn away from the Sun in a matter of minutes. In the final hour, the force shreds planets themselves, mountains, oceans, and continents ripped apart as expansion outmuscles gravity. Then, in the last unimaginable moments, atoms themselves would unravel. Electrons ripped from nuclei, protons torn apart, even quarks separated as space-time stretches faster than the speed of light. The universe would end not with fire or ice, but as a thin, cold gruel of disconnected particles forever flying apart. Timeline: roughly 22 billion years from now, a blink in cosmic terms. But here's the twist: phantom energy isn't just a sci-fi apocalypse. Some measurements of dark energy's behavior, like those from the Dark Energy Survey, hint that its strength might not be perfectly constant. If it's even slightly increasing over time, the Big Rip becomes inevitable. It's like discovering your car's gas pedal is stuck, slowly now, but soon unstoppable. Critics argue that phantom energy violates certain energy conditions in physics, making it less likely. But in a cosmos where 95% of the universe is invisible dark matter and energy, can we really rule anything out? The Big Rip forces us to confront a chilling possibility, that the universe's fate isn't just expansion but dissolution, not a fade to black but a scream into silence. Imagine a cosmic fountain where black holes gulp down matter with relentless hunger. their white hole counterparts might be erupting fountains, spewing out energy and matter in an unstoppable torrent. This is the daring idea behind the white hole eruption theory, which flips the script on the Big Bang by suggesting our universe wasn't born from a singularity, but from the violent outburst of a white hole, the theoretical antithesis of a black hole. Black holes are cosmic vacuum cleaners, sucking in everything that crosses their event horizon, including light itself. But general relativity, Einstein's masterpiece, hints that the math could work in reverse, a region of spacetime where matter and energy explode outward, impossible to enter, only to exit. Picture a black hole running backward in time. A white hole would be its mirror twin, a cosmic geyser blasting material into existence rather than devouring it. And if one of these erupted with enough force, the result could look suspiciously like the Big Bang. The elegance of this idea lies in its simplicity. No need for singularities or mysterious pre-existing conditions, just a white hole's natural explosive behavior, birthing spacetime in a single cataclysmic event. Some models even suggest that every black hole in our universe could, in some higher dimensional framework, be connected to a white hole elsewhere, turning the cosmos into a vast network of cosmic recycling plants. Matter falls into a black hole here, only to be vomited out as a white hole in another universe. It's a tantalizing symmetry, one that could solve the singularity problem while linking our origins to the broader multiverse. So why haven't we spotted any white holes? The answer might lie in their fleeting nature. Unlike black holes, which can persist for eons, a white hole's explosive energy release could make it inherently unstable, collapsing almost instantly after its outburst. The Big Bang itself might have been the last gasp of a white hole, a one-time eruption that birthed our cosmos before vanishing forever. Alternatively, white holes could be hiding in plain sight. Some theorists speculate that gamma-ray bursts, the most energetic explosions in the universe, might actually be the death throes of white holes lighting up the darkness. There's a poetic irony here. Black holes are cosmic tombstones, but white holes could be cosmic wombs. The universe's violent beginning might not have been a singular, inexplicable event, but the natural consequence of a process we're only beginning to glimpse. And if white holes do exist, they could rewrite more than just our origin story. They might be the key to understanding how universes live, die, and are born anew. Until then, they remain one of physics' most tantalizing ghosts, a shimmering possibility just beyond the edge of our telescopes. Imagine a clock that ticks forever, not with gears and springs, but with the very fabric of reality itself, cycling through states without ever winding down. This is the mind-bending essence of time crystals, structures that break time's symmetry by oscillating indefinitely without energy input. Now stretch that idea to cosmic scales. What if the universe's first moments were shaped by these bizarre, self-repeating quantum objects? Some physicists propose that time crystals could have been the universe's first clock, their eternal rhythms imprinting order onto the chaos of creation. Time crystals aren't science fiction. First theorized in 2012 by Nobel laureate Frank Wilczek, they're a new phase of matter where particles lock into a repeating dance, returning to their starting configuration over and over like a celestial metronome. Unlike ordinary crystals, which repeat in space, time crystals repeat in time, a perpetual motion machine permitted by quantum mechanics. In labs, scientists have created tiny versions using chains of ions or diamond defects, observing their eerie clockwork behavior. But in the early universe, these structures might have formed naturally, woven into spacetime itself by the extreme energies of the Big Bang. Here's where it gets cosmic. If time crystals flickered to life in those first instants, their rigid, repeating patterns could have acted as scaffolding for the universe's structure. Picture a vast, pulsating lattice, each tick nudging matter into place, amplifying quantum fluctuations into the seeds of galaxies. This wouldn't just explain the universe's large-scale uniformity, it could reveal why time has a direction at all. Normally, physics treats time as symmetric, but time crystals break that symmetry, creating an arrow by their very existence. They might be the reason we remember the past but not the future, turning the Big Bang's fireball into a story with a beginning, middle, and eventual end. Critics argue that time crystals are too fragile to survive the universe's violent birth. Yet if they formed as topological defects like cracks frozen into space-time as it cooled, their influence could persist long after they dissolved. Others suggest dark matter itself could be a relic of these primordial timekeepers, their oscillations still echoing unseen through the cosmos. Whether they're a footnote or a foundational force, time crystals force us to rethink reality's most basic rhythms, not just how the universe is, but how it ticks moment after moment into eternity. What if the universe isn't made of matter or energy, but of something far more fundamental, pure, unshakable mathematics? This is the wild claim at the heart of the mathematical universe hypothesis, where physicist Max Tegmark proposes a staggering idea. Reality isn't just described by math, it is math. Every star, every atom, even your fleeting thoughts, might be nothing more than intricate equations playing out in an eternal, abstract space. Tegmark's vision strips away the layers of physics, chemistry, and biology to reveal a cosmos that's fundamentally numerical. Think of it like a video game. The graphics, sounds, and story feel real, but beneath it all, they're just code executing on silicon. In this framework, our universe is the output of an unimaginably complex mathematical structure, one that exists independently of any physical substrate. The laws of physics aren't rules imposed on reality, they're the immutable properties of the equations themselves. Gravity isn't a force, it's a geometric relationship. Electrons aren't particles, they're solutions to wave functions. Even time might be an emergent property of deeper mathematical symmetries. This raises a mesmerizing question. Could all possible universes already exist as mathematical structures, waiting to be rendered by observation? Tegmark argues yes, just as the number pi contains every possible sequence of digits, every phone number, every Shakespeare sonnet encoded somewhere in its infinite string, the mathematical universe might contain every possible physical reality. Our cosmos, with its specific constants and laws, is simply one slice of an infinite mathematical landscape. There's no why to our universe's parameters. They're just the ones we happen to inhabit, like finding yourself in a randomly selected room of a boundless library. But here's where the debate ignites. Critics push back, asking how abstract math can feel like the warm sun or the taste of chocolate. If reality is pure mathematics, where does consciousness fit? Tegmark counters that subjective experience might itself be a mathematical pattern, a self-referential computation that creates the illusion of qualia. Others argue this reduces existence to a sterile tautology. The universe is math because math is all there is. And then there's the elephant in the room. If math is all-powerful, why does our universe seem to follow only certain equations? Why quantum mechanics and general relativity, and not some alien arithmetic? Yet the hypothesis lingers because of its eerie explanatory power. It dissolves the mystery of fine-tuning why our universe's constants are so precisely balanced for life. In a multiverse of mathematical structures, some were bound to be hospitable by sheer probability. It also unifies physics' fractured theories under one roof. At the deepest level, everything is relationships, not substances. Even the Big Bang becomes less a creation event and more a mathematical boundary condition, a point where certain equations begin to unfold, the most haunting implication. If Tegmark is right, the universe isn't just knowable, it's inevitable. Every possible reality already exists in the abstract. We don't discover the laws of physics, we stumble upon them like explorers finding pre-written maps. Whether you find this comforting or chilling depends on your appetite for existential vertigo. But one thing's certain, the idea that pi might hold the blueprint for galaxies, for love songs, for the very neurons firing in your brain right now, that's a theory that doesn't just stretch the imagination. It redefines what reality even means. Imagine throwing a party where the guests never leave, they just keep piling up, eating all the food, clogging the bathrooms, and refusing to budge. That's essentially what might have happened in the early universe, thanks to a group of unruly theoretical particles called gravitinos. These pesky leftovers from supersymmetry, nicknamed the universe's bad roommates, could have thrown a cosmic wrench into the delicate balance of the Big Bang's aftermath, nearly collapsing reality before it had a chance to properly begin. Gravitinos are the hypothetical superpartners of gravitons, the proposed carriers of gravity. In the elegant math of supersymmetry, every known particle gets a heavier twin, and gravitinos are gravity's shadowy counterparts. The trouble starts when you consider how they behave in the searing heat of the early cosmos. Gravitinos aren't just heavy, they're also ridiculously stable, barely interacting with other matter. That means once they're created, they tend to stick around forever. And in the universe's first seconds, when energy was abundant, gravitinos would have been churned out in enormous numbers, like uninvited guests multiplying at your party. Here's where the problem gets real. If too many gravitinos lingered, their collective mass would have cranked up the universe's density to catastrophic levels. Picture stuffing an entire galaxy's worth of mass into a space smaller than an atom. That's the kind of gravitational squeeze we're talking about. Instead of gracefully expanding into the cosmos we know today, the universe might have overclosed, collapsing back into a singularity before stars or galaxies could even form. It's like blowing up a balloon only to have it instantly deflate under its own weight. Physicists call this the gravitino problem, and it's a major headache for supersymmetry enthusiasts. The theory is too beautiful to abandon. It elegantly ties up loose ends in particle physics, from the Higgs boson's mass to the mystery of dark matter. But gravitinos are the stubborn guests who refuse to leave, threatening to ruin the whole party. To save the theory, researchers had to get creative. Some suggest gravitinos decayed faster than expected, vanishing before they could wreak havoc. Others propose that the early universe underwent a phase of rapid inflation, diluting gravitinos to harmless levels like opening a window to clear out a stuffy room. Yet the mystery lingers. If supersymmetry is real, where are all the gravitinos? Their absence might hint that they're heavier than predicted, or that some unseen mechanism swept them away. Or worse, it could mean supersymmetry itself is flawed, leaving physicists to wonder if their cosmic party had uninvited guests after all, or if they've been planning the celebration in the wrong venue entirely. Either way, the gravitino problem stands as a cautionary tale. Even the most elegant theories can have messy roommates. Consider this strange but beautiful idea. What if the universe is the ultimate free lunch? That's the essence of the null universe theory, a mind-bending proposition that everything we see, stars, galaxies, even our own thoughts, might add up to exactly nothing. Zero, nada. At first glance, it sounds impossible. How could a cosmos teeming with energy, motion, and complexity possibly balance out to nothing? The answer lies in one of physics' most elegant tricks, gravity's negative ledger. Here's how the cosmic math works. Every bit of matter and energy in the universe carries positive value. The glow of a star, the heat of your coffee, the mass of your body. But gravity, the force that sculpts this matter into galaxies and planets, operates on a hidden ledger. Einstein showed us that gravity isn't just a force, it's the curvature of spacetime itself, and that curvature comes with a cost. The energy required to bend spacetime is negative, like a cosmic debt. And here's the kicker. When you tally up all the positive energy of matter with the negative energy of gravity, the sum cancels out perfectly. It's like having a bank account where every deposit is matched by an equal withdrawal. The balance never changes. Think of it like stretching a rubber sheet. Pressing a marble into it creates a dip. That's gravity's negative energy at work. The marble itself represents positive mass energy. Now imagine the sheet and marble together. the system's total energy is zero because the work needed to create the dip perfectly offsets the marble's presence. Scale this up to the universe, and you've got a cosmos where every star, every black hole, every speck of dust is balanced by the gravitational dent it creates in space-time. This isn't just philosophical sleight of hand. The math holds up. When cosmologists calculate the universe's total energy density, accounting for both matter and the curvature of spacetime, the result teeters tantalizingly close to zero. Even the vacuum energy of empty space, the mysterious dark energy accelerating cosmic expansion, might play into this equilibrium. Some theories suggest dark energy could act as a kind of cosmic overdraft, ensuring the books stay balanced no matter how far the universe stretches. But the implications go deeper than accounting. If the universe truly has zero net energy, it could explain why something arose from nothing in the first place. Quantum mechanics allows particles to pop into existence spontaneously, as long as they vanish quickly enough to satisfy energy conservation. In a null universe, this balancing act isn't a fleeting quantum hiccup, it's the foundational principle of reality. The Big Bang might not have needed an external energy source. It could have been a self-canceling fluctuation, a cosmic coincidence where every positive was matched by a negative. Skeptics raise valid questions. How can we prove the universe's energy is precisely zero, not just very small? And what about regions where gravity seems to win, like black holes? Supporters argue that even black holes obey the rules. Their immense gravitational pull is counterbalanced by the energy it took to crush them into existence. As for proof, some look to the universe's flat geometry. A perfectly balanced zero-energy cosmos should have no overall curvature, and so far, measurements of the cosmic microwave background align eerily with that prediction. The null universe theory doesn't just simplify cosmic bookkeeping, it redefines existence itself. If true, reality isn't a grand explosion of energy but a delicate dance of opposites, a shimmering illusion where every creation is paired with its shadow. It's a humbling thought. Everything we cherish, everything we fear, every galaxy and atom and fleeting moment might all be part of nature's ultimate zero-sum game. Deep in the equations of particle physics, there's a particle that should exist but stubbornly refuses to show up. It's called the magnetic monopole, and its absence has been haunting physicists for decades. Picture a magnet, snap it in half, and you don't get isolated north and south poles. You get two smaller magnets, each with both poles intact. But what if you could find a lone north or south pole, a particle with pure magnetic charge? That's the monopole, a cosmic rebel that defies everything we know about magnetism. The hunt for these elusive particles began with grand unified theories, ambitious frameworks trying to merge electromagnetism with the strong and weak nuclear forces. These theories predicted that in the searing heat of the early universe, symmetry-breaking phase transitions would have created defects in spacetime, like cracks forming in ice as it freezes. Monopoles were one such defect, cosmic relics forged in the first fractions of a second after the Big Bang. The math was clear. If GUTs were correct, the universe should be swarming with them. Yet after decades of searching in particle colliders, ancient rocks, even moon dust, not a single monopole has been found. Their absence isn't just a curiosity, it's a crisis. The fact that we don't see monopoles forced physicists to scrap early GUTs and rethink the universe's infancy. Enter cosmic inflation, the idea that the universe expanded faster than light in its first moments, diluting monopoles to near zero density. Inflation solved the monopole problem, but at a cost. It meant these particles weren't gone, just hideously rare, lurking in the cosmos like needles in a galactic haystack. So where could they be hiding? One tantalizing possibility: cosmic strings, these hypothetical thread-like defects in spacetime, leftovers from the universe's violent birth, might act as monopole traps. Picture a cosmic necklace with monopoles strung along its length like beads. If strings exist and some gravitational wave detectors are searching for their signatures, they could be the key to unlocking the monopole mystery. Then there's the extra-dimensional escape hatch. If monopoles are tucked into rolled-up dimensions beyond our perception, as some string theory models suggest, they might only reveal themselves under extreme conditions like inside black holes or during high-energy collisions at future particle accelerators. It's a long shot, but the stakes couldn't be higher. Finding even one monopole wouldn't just validate decades of theoretical work, it'd rewrite the rules of electromagnetism and offer a glimpse into the universe's most hidden symmetries. The irony, monopoles were once considered inevitable. Now they're the universe's most notorious no-shows, but in their absence they've taught us something profound. Sometimes what we don't find reshapes our understanding more than what we do. Whether they are hiding in cosmic strings, extra dimensions, or simply waiting for a sharper experiment, monopoles remain one of physics' greatest unfinished stories, a reminder that the universe still holds cards it hasn't shown us. What if the universe isn't just hurtling toward chaos, but racing toward a moment of transcendent awakening, a single, all-encompassing point where consciousness becomes the fabric of reality itself? This is the Omega Point, a theory as poetic as it is audacious, blending theology, physics, and futurism into a vision of cosmic destiny. Jesuit priest and paleontologist Pierre Teilhard de Chardin first proposed this idea in the early 20th century, imagining evolution not just as a biological process but as a spiritual ascent. For Teilhard, every star, every cell, every human thought was a step toward an ultimate convergence, a divine climax where all minds merge into a unified superconsciousness. It's as if the universe, in creating us, was secretly building its own nervous system. Fast forward to the 21st century, and this mystical idea finds an unlikely echo in the work of futurist Ray Kurzweil. His concept of the singularity, the moment artificial intelligence surpasses human intellect, mirrors Teilhard's Omega Point in eerie ways. Kurzweil predicts a cascade of technological breakthroughs leading to a merger of biology and machine, where human consciousness can be uploaded, replicated, and amplified beyond earthly limits. The end game, a cosmic network of linked minds, transcending physical form to become something akin to Teilhard's divine unity. The language differs. Kurzweil talks of nanobots and quantum computing, not theology, but the destination feels strangely familiar, a universe waking up to itself. The physics behind this isn't purely fantasy. Some cosmologists speculate that in a universe dominated by dark energy, accelerating toward infinite expansion, there's still a way for complexity to endure. If civilizations harness exponential computing power, they might engineer environments to sustain thought even as stars fade and matter disperses. Consciousness could become the universe's final artifact, persisting in the dying embers of space-time, inching closer to that ultimate Omega moment. Critics dismiss this as speculative hubris, arguing that thermodynamics guarantees a cold, entropic end. But Teilhard and Kurzweil share a radical optimism. The universe, they insist, isn't just a clock winding down. It's a story with intention, where chaos and chance conspire toward higher order. Whether you frame it as God or the singularity, the Omega Point challenges us to ask, is the cosmos merely a machine, or is it something more, a mind in the making, straining toward its own apotheosis? The answer, perhaps, lies in the strange alchemy of stars and silicon, spirituality and science, all spiraling toward an unknown horizon. Imagine peeling back the layers of reality like an infinite cosmic onion. What if everything we perceive is just the surface ripple of something far deeper? This is the heart of physicist David Bohm's Implicate Order, a radical vision where the universe isn't made of separate objects but of endless folds in a hidden fabric. Think of it like a hologram. Shine light on a holographic film, and a three-dimensional image springs to life. but the true information isn't in the image, it's encoded in the interference patterns on the flat surface. Bohm suggested reality works the same way. What we see, stars, galaxies, even our own hands, are just unfolded projections from an underlying dimension where everything is seamlessly connected. Bohm's inspiration came from a chilling realization in quantum mechanics. When two particles become entangled, they instantly react to each other's state, no matter how far apart they are. Einstein called this spooky action at a distance, but Bohm saw it as a clue. To him, the particles weren't communicating faster than light. They were never truly separate to begin with. The apparent distance was an illusion, like two whirlpools in a river that seem distinct but are just expressions of the same flowing water. In the implicate order, every particle, every thought, every galaxy is intimately linked, their separateness merely a trick of perception. To grasp this, picture reality as an endless sheet of paper being folded into origami. The creases represent the implicate order, the hidden structure. When you unfold a section, a crane or flower appears to emerge as an independent object, but it's still just part of the same paper. Similarly, Bohm argued, the universe unfolds from its hidden layers into the explicate order we experience, the world of tables, trees, and telescopes. Even time might be an unfolding, with past, present, and future coexisting in the implicate realm like all possible folds in the paper, waiting to be revealed. This idea reshapes how we view the Big Bang. Instead of a singular explosion, the universe's birth could be an unfurling from the implicate order, a single fold giving rise to the illusion of space, time, and matter. Black holes might not destroy information but re-enfold it, tucking stars and galaxies back into the hidden fabric. And consciousness, Bohm speculated it plays an active role in the unfolding, that observation isn't just passive witnessing but a participatory act in creation itself. Critics dismiss the implicate order as metaphysics masquerading as physics. It's elegantly untestable. Yet its echoes appear in modern holographic theories and quantum gravity. Whether a profound truth or a poetic metaphor, Bohm's vision challenges our deepest assumptions. What if reality isn't built from pieces but unraveled from wholeness? The universe might not be a collection of things but a single verb, an eternal act of becoming, flickering into focus one fold at a time. Now let's end with perhaps the most humbling idea of all. What if consciousness isn't something the universe has, but something it is? This is panpsychism, the radical notion that even the tiniest particles in existence, every electron, every quark, carry some faint spark of awareness. Not full-blown human thoughts, of course, but a raw, primal form of experience, like the dimmest glimmer of sensation in the void. Imagine each atom in your body as a microscopic sentry, not just mindlessly obeying physical laws, but feeling its existence in some ineffable way. Then picture those atoms linking up, forming molecules, cells, neurons, until suddenly, the sum of their proto-consciousness becomes you, reading these words right now. This isn't just philosophical musing. Modern panpsychists like philosopher David Chalmers argue that consciousness might be as fundamental to reality as space or time, a property woven into the fabric of existence itself. Think of it like mass or charge. You don't create mass by arranging atoms a certain way. It's already there, intrinsic to the particles. Similarly, consciousness might not emerge from complexity. It might be there all along, just waiting for the right organization to amplify it. The implications are staggering. A star wouldn't just be a ball of plasma. It'd be a slow, roaring dance of elemental awareness. A black hole wouldn't just warp space, it'd warp experience. But here's the real cosmic twist. If panpsychism is true, the universe might not need observers to collapse quantum probabilities or give meaning to existence, because it was already awake in some rudimentary way from the very first moment. The Big Bang wouldn't just be the birth of matter and energy, but the awakening of a universe-sized mind, unfolding from simple particles to complex beings capable of reflecting on their own origins. In this view, human consciousness isn't an accident, it's the cosmos gradually turning its gaze inward, a billions-year process of self-recognition. Critics, of course, scoff at the idea of conscious electrons. How could something so small feel anything? And if everything is conscious, why don't rocks or clouds exhibit signs of thought? Panpsychists counter that complexity matters. Just as trillions of water molecules create an ocean's waves, trillions of conscious particles might create full awareness. Others argue we're trapped in an explanatory gap. We can describe brain activity, but we still don't know how subjective experience arises from mere matter. Maybe it doesn't arise at all. Maybe it was there from the start. The beauty of panpsychism is how it reframes our place in the cosmos. We're not strangers in a dead universe. We're the universe itself, grown curious enough to ask questions. Every thought, every emotion might just be nature's way of remembering itself. So the next time you gaze at the night sky, consider this: those distant stars aren't just burning gas. They're echoes of the same primal awareness that lets you wonder about them, an endless loop of a universe whispering secrets to itself, one conscious moment at a time. From the eerie possibility that we're living in a hyper-realistic simulation to the mind-bending notion that our universe is just a holographic projection, we've explored cosmic ideas that stretch the limits of imagination. We've wrestled with the paradox of time crystal structures that tick eternally without energy, and danced with the idea that black holes might be cosmic wombs, birthing fresh realities in their crushing depths. We've stared into the void and wondered if the Big Bang was just one bounce in an endless cycle, a universe collapsing and rebounding like a cosmic heartbeat. And let's not forget the unsettling allure of Boltzmann brains. The statistical nightmare that suggests your thoughts right now might be a fleeting accident in an infinite sea of chaos. Each of these theories isn't just wild speculation. They're windows into humanity's relentless drive to understand existence. The simulation hypothesis forces us to question the very fabric of reality. The holographic principle turns galaxies into pixels on a cosmic screen, and the bouncing universe, it rewrites death and rebirth as the universe's natural rhythm. These aren't just ideas, they're invitations to rethink everything we thought we knew. So here's the real question: which theory shook you to your core? Did the multiverse's infinite possibilities leave you dizzy? Or did the ghostly whispers of Penrose's cyclic cosmology resonate deeper? Drop your thoughts in the comments. We're all cosmic detectives here, piecing together the universe's greatest mysteries. And if your curiosity isn't satisfied yet, hit subscribe. The universe has endless secrets, and we're just getting